Hi, it's Mike Sklash here. I'm a senior hydrogeologist for the Dragon Corporation, um, and I just want to talk a little bit about nailing it down, some tips for a solid site characterization to make sure that you have the best possible understanding of a site and you're ready to go to remediation. So, just a little background on me. A Bachelor of Applied Science in Geological Engineering, a PhD in Earth Science, where I specialized in hydrogeology. Got that at Waterloo in 1978. I was a professor at the University of Windsor in geology and environmental engineering from 1977 to 94. I left academia to become a consultant, started working with Dragon in 1992 full time. And while I was at Dragon, I was also an adjunct professor at Lawrence Technological University. I do expert work in the United States and Canada, and that consists of doing things like expert testimony, peer review, and things at a very high level. Um, so just going to the next slide. This is you. If you're listening to this, you're probably frustrated with your current site investigation progress or the progress of remediation or the cost of remediation. You would consider alternate methods of site investigation if it would lead you to a better experience in remediation, and you would consider a second opinion or a review. I'm going to go over a bunch of things that I've learned and used over the past several years, and hopefully that will help you move along in your investigation or remediation. So typically we use things like Darcy's Law and other basic hydrogeologic approaches to figure out the nature and extent of contamination. We drill holes, we sample soil, we test soil, we install boreholes, our monitoring wells, we measure water levels, we figure out groundwater flow directions, we measure permeability. So that's what we typically do when we're characterizing a site. What else can you do to nail it down, to be more certain of what you find? And the idea is to nail it down so tight that you get the characterization right the first time. So I'm going to talk about techniques that give you more coverage, more detail, and make you more confident about the results you have so you can go on to the next step. So how do we get there? Two questions I ask myself. I ask, how well do my puzzle pieces fit? Does my geology make sense with my groundwater flow rates? Does the distribution of chemicals make sense with the direction of groundwater flow? These are common things that hydrogeologists do. And then I ask, would it help if I had more puzzle pieces, some other tools that would make things clearer and more definitive? So I'm going to go through a few case studies very briefly to introduce you to some of the techniques. And I want you to know that the client for each of these case studies thought their consultant was getting it right the first time. Each of these case studies began as a peer review that we did. So this is a site in the Midwest that is kind of interesting, case study number one. And this subdivision was an area where people used wells, individual wells, to get groundwater, and they found TCE in the groundwater. TCE is a degreasing solvent that is a problem in groundwater, a common problem. Um, to the west of the subdivision was our client eventually. We did a peer review on this site. They made aluminum tubing, and at one time had used TCE, or at least the predecessor had used TCE at that site. To make it complicated, there was another manufacturer that was adjacent to the subdivision that also made aluminum products and also used TCE. So we got involved, we did a peer review, and this is kind of what we found. The national consultant that had worked on this, spent a fair amount of money, came up with this conclusion. The groundwater flow velocity in the local aquifer was calculated to be approximately 2,900 feet per year. That's really fast. That's faster than possible. So the client was worried about regulator legal action because of the TCE and the adjacent residential subdivision, but also the national consultant come up with a fairly expensive cleanup project based on their misunderstanding of the hydrogeology of the site. This is a conceptual site model of the site, and you can see that there's an aquifer and another aquifer, and I've got some groundwater flow arrows on here. The residential subdivision would be over here on the right. This is our interpretation. And what the other consultant had missed was this aquitard, that they assumed that the deeper sand were connected, and that's how they got the groundwater flowing so fast. So this was just a standard, very detailed investigation that we did, but we made sure that all the puzzle pieces made sense. The national consultant, spending lots of money, didn't do that. So I'm going to talk about case study 2, and this is where we get into some very detailed techniques. So this is a site that we're working on in Salina, Kansas, and the area off to the west here at one time was an Air Force base. It was the Schilling Air Force Base, which during the 1960s was a strategic air command base. It was used for bombers to run missions, and they would come back and the planes would be cleaned with TCE. At that time, they didn't know how much of a problem TCE could be. They just let it run off the planes onto the ground, into the ground. The problem is that the groundwater flow direction is from the Air Force Base towards the city of Salina well field. So that's generally the problem, but the geology is extremely complex. So to find the TCE plumes so that we could put our arms around it, understand the size and depth and how fast they're moving and so on, and then eventually to remediate is problematic because of the geology. We basically got two creeks, Dry Creek and the Smoky Hill River, that have formed the geology, which is a meandering stream geology. So where can the TCE plumes be? So this is a close-up of part of Smoky Hill River, and these big loops that you might see sometimes when you're flying. Rivers tend to do this when they're going over flat terrain. They're called meanders. The outside of meander, the water in the stream is moving quickly and would carry fine particles. But the inside moves slower and larger particles are carried. As a result, you get different areas that have fine-grained sediments and those that have coarse-grained sediments. And the coarse-grained sediments are going to be the ones that are going to conduct groundwater flow and contaminants. The problem is it's not just a complex two-dimensional problem. It's three-dimensional. This cartoon shows meanders with the lighter color ones being the more recent and the darker color ones being the older meanders. So even though you may have sand at a certain location on the surface, 10 feet down you might not have sand, you might have clay. 10 feet further down you might have sand. And we don't know the connections between these sands. This is not our problem. This is the lower Mississippi. It's a U.S. Geological Survey old map of showing the meander bends there, but it gives you the idea of the complexity that you're faced when you need to know where the groundwater is going to flow, where the chemicals are going to be. So we need to delineate my plume in salinum. How are we going to do that? We need to remediate my plume. We need to find out where it is. So this is a technique that we use at the site. It's called the hydraulic profiling tool. It's a tool that Geoprobe has in their suite of tools. Geoprobes make small drills. And the hydraulic profiling tool basically gives us a continuous vertical record of where the permeable zones are. As you push it down, it gives you information real time. And on the right, we see the hydraulic profile tool. And the hydraulic profile tool basically does two things. It records the conductivity of the material it's moving through, the electrical conductivity, and that can be related to the geology. And this log here we see, which is about 60 feet deep, has the electrical conductivity with low conductivities on the left, high conductivities on the right. And so these soils that we see up here have a high conductivity. They would probably be clays. And the low conductivities will be sandy soil, so they would be the permeable parts. The next panel is the actual HPT pressure log, and the HPT will try to get water into the formation. The more permeable the formation is, the lower the pressure reading. The less permeable, like the clays, you get high pressure. So we see high pressure up here and low pressure here. And so that's telling us again, it's consistent with the electrical conductivity where the permeable zones are. One of the other things you can do with the HPT is get a log of hydraulic conductivity with, that's the third panel, the one on the right, with the low hydraulic conductivity on the left and the high hydraulic conductivity on the right. And we can see some low conductivity layers and some high conductivity layers. So if we want to determine where the water's moving and hence where the chemicals could be moving, we need to do something like this to get lots of detail, more detail than we could get if we were using conventional techniques. So case study 3 is a technique that we use to help in delineating plumes without a drill rig in areas where maybe you can't get a rig in, or areas where you need real high areal density of of information. And we call this passive soil gas survey. On the left, you see a passive soil gas probe. We use a company called P.Eng out of Maryland for these probes. We drill holes in the subsurface. We open up our probe gas probes and hang them in the hole for maybe 2 weeks or so. Let them adsorb volatile gases, things like TCE or benzene, and we retrieve them and we have them analyzed by Beacon, who desorbs the organics and provides us with data and maps. So this is a site where we worked on a grid that was as small as 2 meters across, as big as 5 meters across, where we wanted to get extra detail around a certain location. And this is location where there was high TCE. And what we see here is a bullseye indicating a local source, probably. It's another TCE case where we had a potential source on the west or left side. We have another high TCE on the right side or east. The groundwater flowed from northwest to southeast. So the question is the high concentration indicated on the right side or the southeast corner related to that in the northwest corner? And the previous consultant working on the project had done a lot of drilling in the area. This is fractured bedrock that the groundwater is moving in, and they thought that they did a pretty good job and agreed that they did do that. But the regulators hesitated. They thought that perhaps there were unknown, undiscovered preferential pathways that would allow the chemicals to cross the road. So we did this high density survey of the soil gas, and you can see that along the side of the road between the potential source and the high spot on the southeast corner, there's low concentrations. So what that is indicating is that the high spot in the southeast corner is in fact its own in separate source, not connected to the one to the northwest. We can also do studies to figure out where did the water come from. Now this is more a broader approach using really global understanding of the nature of precipitation and the isotopic composition of water. So this is a question that we commonly deal with here is when we find nitrate in the groundwater or in surface water, is it coming from recent practices, current practices, or old practices? We call that legacy nitrate. So how can we tell where that water's coming from in the stream? And is the nitrate old or new? So one of the things that we can use are isotopes in the water molecule. And we can distinguish between old water and new water, meaning current storm or snowmelt event water. Groundwater tends to be a homogenization of precipitation over a longer period of time. So isotopes, if you're not familiar with them, are like versions of an atom. They have the same chemical properties but different physical properties. And in the water molecule, we have 3 isotopes of hydrogen that we can use and 2 isotopes of oxygen that we can use for tracing water. And what we're going to talk about basically deuterium to protium ratio and the oxygen 18 to oxygen 16 ratio. So this is showing the oxygen 18 concentration with time from, looks like about 1963 to 1980 at Midway Airport in Chicago. And we don't have to worry about this concentration notation. But know that these fluctuations, which look like they're 15 units each year or so, are much greater than the analytical precision. So these are real differences. If we look on an annual basis, this is what it looks like at Chicago on average, that in the winter, we have values down here and down here, and in the summer, we have values in here. So there's a large change based on temperature that occurs over the year in the precipitation. But the groundwater will tend to take on an average. And in the Chicago area, it might be somewhere between -8 and -10 or so in the groundwater, which is kind of a weighted mean average of the precipitation. So often what we look at is comparing the oxygen 18 to the deuterium concentration. And across the globe, waters tend to follow a meteoric water line. That just means waters that are not evaporated. And they have a specific slope. Globally, it's about 8. But specific areas can have a slightly different slope, as this does. These MWs are monitoring wells A to F. These are at an agricultural site. And they're showing that there's a bit of a range in deuterium and oxygen 18 in the groundwater. These are two wells that are really interesting, monitoring well J, that we took, which is just one of the monitoring wells there. But this area, when it rains, you get ponding of surface runoff, and you get preferential recharge in that area. So this is what happened after a big storm. So this is the pond values down here. So these were water samples taken from the ponded rain, and these are the groundwater samples that used to be up here. So we had this major shift very quickly at this place where the water table is about 20 feet below ground. But still, because of the very rapid recharge, we've affected the quality here. So we need to realize that some wells will change quality, but won't be representative of the groundwater. They'll be representative of rapid recharge. So that's telling us old versus new water. These are old water. This water is easily affected by new water. So 3 takeaways I'd like you to look at. When you're looking at your site investigation remediation, do all your puzzle pieces fit? Would more puzzle pieces help to nail it down for you? And would more coverage and more detail facilitate closure at your site? And another takeaway that I haven't got on here is, would you think that a second opinion or a peer review might be useful to see if you can answer these first 3 questions? So wanted to thank you for watching. You can check out some of our videos on our website. We talk about isotopes. We talk about this, the Salina case study, and you'll find some other interesting things on the website. So thanks again for watching.